Okay, let's get started. We will come back to this at the end of class. First of all, course announcements. Problem set 2 is due today at 11:59 p.m. Montreal time. Feel free to post in the Slack with any last-minute questions. Likewise, feel free to, again, discuss with collaborators. There'll be no class on Monday because it is Thanksgiving. I hope that everyone has a good Thanksgiving. I'm American, so it feels weird to me that Thanksgiving is this earlier in the year, but yeah. Are there any questions about the course? Americans have a different date for Thanksgiving. It's still a thing in America, but it's a different day of the year. Yeah, and Canadians don't, it's not as big a thing for Canadians as much. Okay. Let's carry on with Taylor series, which we started last time. So as a reminder, what a Taylor series is sort of the limit of these polynomials, which are approximating a function up to kth derivatives. The kth Taylor polynomial, p sub k, is the polynomial that matches the derivatives of f up to derivative k at this particular point. Here I've picked the point x equals 0. So that was something we discussed last time. And then the limit of infinite degree is the Taylor series, which is this infinite series, which in some cases will converge to a value. So I said some confusing things last time about the convergence of Taylor series, and I'm sorry. I will try to spell everything out now and make it be completely right. So at least for x close to 0, we have f of x being exactly the limit of this infinite Taylor series. The infinite Taylor series is not an, again, it's not an approximation to f. It is literally equal to f. You can do a Taylor series about x equals 0. We're not going to be talking really about Taylor series around other points, but you can also do that. Again, the things to bear in mind is, as long as this infinite sum converges, it is like, as long as it is a well-defined number, it is going to be equal to f of x. There will be situations where it doesn't converge for some values, and we'll see some of those later today. For some functions f of x, it converges for all x. Like, for example, for the exponential function, the Taylor series converges for all x. For other functions, it will converge just for x in a particular interval called the interval of convergence. And there's like, sometimes you can think of a convergence radius. And we can see that too, though I'm not really going to go into that. But basically, you should think of a Taylor series as another way to write down the function, and it will be exact, and it will work fine at, in this case, x equals 0. But if you go too far away from x equals 0, it's not like it will be a bad approximation. It's just this series won't make sense in just the way that 1 minus 1 plus 1 minus 1 plus 1, which we saw last time, didn't make sense. It's not that it didn't, it's not that it was the wrong number. It's that it wasn't any number at all. So if a Taylor series is any number, it is the correct number. But sometimes it just doesn't converge. And that will hopefully become a little bit clearer later on. But for now, just think of this as another way to write down the function f of x. Are there questions about this before we get into some examples? Hopefully it'll be a bit clearer with examples. Okay, let's go on. So this is, again, the definition of the Taylor series. So what is the Taylor series for e to the x around x equals 0? How would we go about doing that? How do we find it? suppose someone gives you a function and they want you to create a Taylor series for it. Yeah, so we can just calculate the derivatives at 0, which is what is going on in this definition. And we can use the fact that the derivatives are of e of x are e to the of e to the x are e to the x. However many derivatives you take, you just keep on getting e to the x back. So that means that if you evaluate all of these at x equals 0, then you're just going to get e to the 0, which is 1. So evaluated at 0, all of the derivatives are 1, which is cool. This is the only function for which that's the case. And in fact, the Taylor series is the proof of that. So we just plug these in, and we get the Taylor series is this. So 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x fourth over 4 factorial. Remember the factorials whenever creating a Taylor series. Remember to divide by the factorials. It's important. And what I just said about it being the Taylor series is a proof of the fact if you had any function that has this property where all of the derivatives are equal to 1, then this has to be the Taylor series for that function. And since this Taylor series converges to e to the x, that means that the only function that has all of those derivatives equal to 1 is e to the x. There's a question. If the Taylor series is a proof of that, why are we allowed to use that fact to do the proof? I think I might have just answered that question. I'm not sure. Cool. OK, so what can we do with e to the x being this? We will see so many things that we can do with this. But just to start us off, we can just plug in some numbers. We can plug in, for example, 1. And we get this beautiful representation of e, which is another definition of e. You will sometimes see this is the definition of e, which is 1 plus 1 plus 1/2 plus 1 over 6 plus 1 over 24 plus 1 over 120 and so on. The sum of the reciprocals of all the factorials from 0. And then you can also do 1 over e, which is this. And it's not at all clear that these two things are reciprocals of each other, by the way. Like, if somebody gave me this thing, I wouldn't be at all clear. I wouldn't immediately know that this multiplied by this equals 1, but it does. And so you could use this if you wanted to approximate any power of e. It's not necessarily the fastest way to approximate powers of e, but it is a way to approximate powers of e. OK, we will see more applications of this in a moment, but let's go on to other Taylor series. Let's do Taylor series for polynomials. What is the Taylor series at x equals 0 for the polynomial, this polynomial? This may be a trick question. Like, it's perfectly well defined. There is an answer. Yeah, so let's go into this. Oh, there's a great question. What is x sub 1? That's a typo. It should just be x here. So let's take some derivatives at 0. So derivative at 0, just the function evaluated at 0 is going to be the constant term. If you take the derivative evaluated at 0, then you get this. And so the constant term of that polynomial is just a1. Notice that it's really easy to evaluate what a polynomial is at 0. You just take whatever the constant term is, because all the other terms cancel out. So here you have a0, a1. The next one becomes 2a2, because you took the derivative of a2 times x squared twice. Now, then you have 3 times 2, a3, which is the third derivative of x cubed times a3. Because you went from x cubed to 3x squared, from x cubed to 3x squared to 6x to this, to 6 times a3. And in general, you're going to get k factorial ak. And you can keep on doing this up until the point at which you sort of run out of terms in your polynomial, at which point all the derivatives become 0. If you take n+1 derivatives of a degree n polynomial, you end up with 0, because you've just differentiated all of the terms that way, basically. And then look, n factorial over n factorial, 2 factorial over 2 factorial. All of these things cancel out. So what do you have? Well, you have the polynomial itself. And maybe this shouldn't be surprising, because remember, the way we went about creating a Taylor series, we were like, oh, we're going to create these polynomials that approximate the function. Well, if your function is already a polynomial, then clearly the best approximation to it by polynomials is itself, which is a perfect approximation. So the Taylor series is actually finite if it's a polynomial, and it's just the polynomial. Are there any questions? I love the way that math has these circles where you can go around a chain of logic and come back to where you started, and you're like, oh, wow, it works. It's great. OK, so let's move on. Let's look at the log. Now, what is the Taylor series for log of 1 plus x? And the reason I'm doing 1 plus x is because log x wouldn't work around x equals 0, because it is not defined. Log of 0 is just not a thing. Any thoughts? Start going through it. I realize you won't have been able to go through all of the derivatives. So if you have just the function itself, it's log of 1, evaluated x equals 0. So that's 0. If you took the derivative of this first, you'd have 1 over 1 plus x, evaluated x equals 0. And that's equal to 1. If you did the derivative twice, you would have the derivative of this. And that is going to be -1 over 1 plus x squared. Why is the derivative of log of 1 plus x equal to 1 over 1 plus x, though? Remember, we found that the derivative of log of x was equal to 1 over x before. Yeah, we can use the chain rule. log of x, log of 1 plus x, the derivative is equal to the 1 over 1 plus x times the derivative of 1 plus x. But the derivative of 1 plus x is just 1. So yeah, this is 1 over 1 plus x. Same thing. In order to get the derivatives of 1 over 1 plus x and so on, we can just use the chain rule again. So we have here -1, which is the exponent. This is 1 plus x to the -1. So to get the derivative of it, we get 1 plus x to the -2 times -1. To take the derivative of that again, we have 1 plus x to the -3 times -1 times -2. So here we are multiplying by the exponent here. So this is -3. So we multiply by -3, we get -3 factorial. Now we multiply by -4, and so we get 4 factorial. So these are going up as factorials, and they're swapping sign each time. This is just the chain rule. And applied to 1 over x to the n, the derivative of 1 over x to the n is just equal to -n 1 over x to the n plus 1. Okay, so now we have these derivatives. What can we do with them? We can plug them into a Taylor series. So what do we get with the Taylor series? What are the first few terms? Again, this was the... Be careful with your indexing. The factorials are not necessarily synced up with the factorials in the denominators. It's still a pretty nice Taylor series. Thoughts? First 3 terms? Nobody? Cool, there are some terms. Yeah, so let's write this out. We can take the first few terms here, and we can see that the first thing is just 0. There's no constant term. Then there's a 1, -1 factorial over 2 factorial, plus 2 factorial over 3 factorial, -3 factorial over 4 factorial. It's a little bit thorny, but basically all we have is just 1 over n with the signs changing. So it's very pretty. It's because we had n minus 1 factorial over n factorial. So this is very, very important to if you are proving this, to be very careful about your indexing. Make it clear that you have n minus 1 factorial on the top. Anyway, so this is an example of a Taylor series that doesn't converge for all x. Also, this is a really nice Taylor series. As an example of something, one of the reasons why it's really nice, what would happen if you put in 1, just x equals 1? You would have log 2. So log base e of 2, and that's equal to 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5. And yeah, that's really cool that you have this infinite series that just happens to have this really nice, it converges this really nice number, log of 2. Anyway, but this is an example of a Taylor series that doesn't actually converge for all x. For example, if you put in x equals 2 here, this makes us sad. The reason is these things are getting big. Like 2 to the 5 is much bigger than 5. 2 to the 100 is way bigger than 100. And so if we thought that 1 minus 1 plus 1 minus 1 is bad, this is way worse because these terms are getting bigger. as you're adding a big thing, then you're taking away an even bigger thing. You're adding an even bigger thing. If you sort of plot this, what's happening to the sum, it's like oscillating way off to infinity. So this is an example of a Taylor series that does not converge if you take x equals 2. But it does work if x is between, in this case, it's bigger than -1 and less than or equal to 1. That will work. The interval of convergence differs between functions. For e to the x, for example, it converged for any x. But here it converges just in this interval. Are there questions? Not equal to -1. If you set equal to -1, you get log of 0, which doesn't work. And that the reason, it's beautiful. The reason why, try plugging in -1 on the right-hand side, and you get 1 plus 1/2 plus 1/3 plus 1/4, and so on. And that is not a convergent series. That actually goes to infinity. And you can prove that it goes to infinity because log of 0 is not defined. So that's a proof that the harmonic series goes to infinity. What's a good way to find the interval of convergence? I'm not going to go into discussing that, but you can go and look it up. There is that will be discussed in various calculus texts and stuff. Yes, it's really crazy that if you go just before -1, it doesn't go to infinity. If you take the Taylor series around x equals a, let's see. If you take the Taylor series around a different a, would the radius of convergence still be 1? No, I don't think so, but it's a really good question. There was a question about Taylor series only using x going to 0. No, a Taylor series is true for other values of x. So here you could, for example, set x equal to 1/2, and it would work exactly. You could also set x equal to 0, and that would work. But you could set x equal to other things. That's sort of the point of a Taylor series. It is not a limit. It's like in the sense of it works for lots of values of x. In the case of e, it works for any value of x. So if you were trying to look at e to the 10th, for example, you could just plug in 10 here, and you would get a series that converges to e to the 10. OK, let's move on. Sine. So we haven't actually yet looked at the derivative of the sine function. So let's look at the derivative of the sine function. We're going to have to prove this. And so what is the derivative of sine? Has anybody seen this before? Yes, it's cosine, which is cool. Why is this true? We're going to use these following limits. And of course, we're going to prove why these limits are true. So let's just walk through the limits before showing how we can prove them and why they're useful here. So the first one is if you take x going to 0 of sine of x over x, that's going to be equal to 1. And this is proved in various ways, but we're going to prove it from first principles. This is an interesting ratio because sine of 0 is 0, and x, of course, is 0 at 0. So it's 0 over 0. Likewise, this is 1 minus 1 over 0. So it's not clear what these limits would be. These 0 over 0 could be anything. 0 over 0 could be infinity. It could be 2. It could be 1. If you have 5 over 0, that's always infinity. If you have 0 over 5, that's always 0. But if you have 0 over 0, you don't know what that is. So we have to work out what those limits are. Now here is a proof. Why is this a proof? A proof of both of these things, in fact. Yeah, so let's look at the first one first. Sine of x over x. So here, this is theta instead of x because it's just thinking of it as an angle. So what is sine of theta over theta? Well, sine of theta is this thing if you're in a radius 1 circle. And in a radius 1 circle, the arc of measure theta is just equal to theta in radians. Sorry, I realize I should have specified here that sine and cosine are now working with radians. In general, we will use radians. I've sort of used degrees and radians interchangeably, unless there's some real reason to be using degrees. I'm just going to use radians now. So radians, the reason why we use radians is because of this, that the arc length is just equal to the angle. So the arc length here is just theta. The height here is sine theta. And as theta gets really, really small, as you can see, this is basically a straight line. And this height is basically the same as the arc length. And this is going to get better and better as an approximation as the angle gets smaller and smaller and smaller. OK, so sine theta is basically equal to theta for theta small. So sine of theta over theta, or sine of x over x, is going to be 1. Now, what about 1 minus cosine of x? Well, 1 minus cosine of x is just this thing. It's the bit here that's part of the radius, because the radius of the circle is 1. And cosine is just this thing in blue. And so it's this little tiny thing. And as you can see, this is moving towards the edge of the circle. So this tiny thing is getting really small. And it's getting small faster than, this is basically becoming a really steep sliver, a really steep, almost a right triangle, basically. And so 1 minus cosine x, this black segment, over x, which is this arc, this is basically like the hypotenuse of a triangle, and this is the near side of the triangle. As the angle of the triangle gets really big, you can think of this as a little right triangle, basically. And so 1 minus cosine of x over x equals 0. Are there questions about this? It doesn't feel like a proof. So if we were actually trying to make this into a proof, we'd have to tighten it up a little bit, only a little bit. So the way in which I would tighten it up is I would basically, I would say something about how the arc length gets closer and closer to a straight line. This arc becomes closer and closer to a straight line. And so the straight line approximation becomes better and better. And then I would have to do a little bit of algebra to make it be more rigorous. But I think that you should, if you're convinced by something like that, there is a proof there. It just sometimes it takes a bit more formal math to make it sort of official. So if something sort of looks obvious, then it's not necessarily a full proof, but it's an indication that there is a proof. The reason why I'm not going into the details here is because I haven't given you the machinery to necessarily write the formal proof here. Like, I wouldn't ask you to write this as a formal proof. But this is really what mathematicians are thinking about if they're writing a formal proof of this. There are two separate things. There's sort of understanding the proof and there's writing it. And here, I hope that you at least sort of understand what's going on. Does that help? Any other questions? OK. So how do we use that? We have these two limits. Let's use them to get the derivative of sine. So let's go back to the definition of the derivative. The derivative of sine of x is the limit as h goes to 0 of sine of x plus h minus sine of x over h. Let's use the sine angle addition formula, which we could prove if we wanted to, but I'm not going to do that. This is the sine angle addition formula for any two angles, x and h. So this is what it's equal to. Ugh, that's a lot of things. But let's write it out in a better way. We can separate this, break it into two fractions. And now it's looking a little interesting. What can we do? What can we do here? How do we make this simpler? Isn't sine addition related to complex numbers? Yes, one way to prove it would be with complex numbers, though you could also, it depends on how you've proven that property of complex numbers. You don't want to have a circular proof where sine addition relies on complex numbers and complex numbers rely on sine addition. Yes, we can factorize both of these. So let's pull out the cosine of x and pull out the sine of x. And we've got suddenly the limits from above here. Yay! So we can just plug those in. Cosine of x times 1 minus sine of x times 0. Done. We have cosine of x. Any questions? I probably shouldn't have written cosine of h. This is like bad notation because there's this thing called hyperbolic cosine, which is written cos h. Where do we get the first line here? This first line is just the definition of the derivative. And then, or unless it was meant this line, which is just the sine addition formula. That's what sine of x plus h is. We didn't prove that here, but it is something that one can just prove. There are ways to prove it using like right triangles and stuff. Okay, so that was the derivative of sine, and just you can work out the derivative of cosine in basically exactly the same way. Not going to make you go through that, but the derivative of cosine is not sine, it's negative sine. But it's just basically exactly the same proof, only using the cosine addition formula instead of the sine addition formula. Okay. So let's work out this Taylor series for sine of x around 0. Sine of 0 equals 0. Sine of the derivative of sine of x is cosine of x. So we have cosine of 0, which is 1. Then if we take the derivative twice, we get negative sine of 0, because derivative of cosine is negative sine. So we have 0 again. Then we have, if we keep on doing this, we have sine, cosine, negative cosine. Then it goes back to sine, cosine, negative cosine. And it keeps on repeating. It's this nice sort of period 4. Sine, cosine, negative cosine. Period 4 is interesting. What else did we see with period 4? Come back to that. You can think about it. Yeah, there's going to be I coming up here somewhere. Period 4, I. I to the 4th is 1. So there is the connection, which we'll make in a moment. But for now, let's just write down the Taylor series. The Taylor series is just if you plug these in, half of the terms cancel out because these are all zeros. So all the even terms in the Taylor series are 0. And the odd coefficients, we just have 1, negative 1, 1, negative 1, 1, negative 1. So we are going to end up with 1 over 1 factorial, 1 over 3 factorial, 1 over 5 factorial, and then with the signs alternating. So that's what it looks like for the Taylor series of sine of x. This is another thing that should teach you that sine and cosine are pretty important functions, that they have really simple Taylor expansions, Taylor series. Okay, let's get cosine similarly. So cosine in much the same way, cosine of 0 is 1. If we take the derivative, negative sine, then negative cosine, sine, cosine, negative cosine. It also oscillates with period 4, which makes sense. It's just the same set of derivatives, just shifted over by 1. Cosine, negative cosine, sine, cosine, negative, yeah. So this is just 1, 0, negative 1, 0, 1, 0, negative 1, 0. And here, we've canceled out all of the odd Taylor series terms, and we end up with, again, alternating positive and negative. So 1 is the constant term minus 1/2 x squared plus 1 over 4 to the 4 factorial x to the 4th, negative 1 over 6 factorial x to the 6th, and so on. Okay. Those are the two Taylor series. Let's take a quick look at derivatives of Taylor series, since we have sine and cosine here. Let's look at what it means to do the derivative of sine equals cosine in Taylor series. We can just take the derivative of the whole Taylor series here. And look, the derivative of x is 1. The derivative of x cubed is 3x squared. So that becomes 1 over 2 factorial x squared. This becomes 1 over 4 factorial times x to the 4th. 1 over 6 factorial times x to the 6th. And look, we have the Taylor series for cosine of x. So the derivative of the whole Taylor series for sine of x is the same as the whole Taylor series for cosine of x. Another one of those things that's just really nice that it works. Okay. What about this? What is the derivative of the Taylor expansion of log 1 over 1 plus x? There are a couple of ways you might get it. Yeah, we can go back to the Taylor expansion for this. There you go. Here it is. What happens if you take the derivative? Yep. So this is what happens if you take the derivative of the whole, sorry, I already had it here. If you take the derivative of the Taylor series of log of 1 plus x, you get 1 minus x plus x squared minus x cubed plus x to the 4th. Now here's the cool thing. This is a proof that this is the Taylor series of 1 over 1 plus x. Okay, so, well, if we substituted in negative y equals x, well, we get 1 over 1 minus y is equal to 1 plus y squared plus y cubed, and so on, which is just the geometric series. So we see that actually this whole geometric series thing, this is another Taylor series. This is the Taylor series for 1 over 1 minus y. All this is infinite series are all connected. I think that's cool, at least. Okay, so this ties in with, there are whole areas of math studying these things. But let's dive into something which you might have seen before, Euler's formula. So why is this only defined on y less than 1? Because this would explode otherwise. If you have 1 plus 10 plus 100 plus 1,000, if y equals 10, for example, then that would not give you a single number at the end. So let's look at those Taylor series for e to the x, sine of x, and cosine of x. We had these 3 Taylor series. They look kind of similar, but there are some sign differences. So some people were suggesting thinking about I. So let's see what happens if you took e to the ix. Well, if you took e to the ix, which that doesn't make sense. I know it doesn't make sense. You've just said, what if you raise an imaginary number, raise e to an imaginary power? Sorry, this should be e to the ix here. We didn't define what that is, but let's see what happens. If you put this into the Taylor series, you get 1 plus ix minus x squared over 2 factorial plus minus I times x cubed over 3 factorial plus blah, blah, blah. This is because I squared is -1, I cubed is negative I, and I to the 4th is back to 1. And then you cycle through again. If you pull out the i's, you get all the real stuff. And that looks remarkably like the Taylor series of cosine of x, plus I times all of the complex stuff, which looks remarkably like all of the stuff with sine, all of the Taylor series of sine. So with this nonsense e to the ix, again, this should be e to the ix, sorry about that, you end up with cosine of x plus I sine of x. Okay, so this is called Euler's formula. And it can be seen as the definition of e to a complex power. You can think of this instead of, we didn't ever say what that meant. Like we defined I by virtue of just saying I squared equals -1. That's all we did to define I. So there's no reason why e to the I has to be anything. But here we can define it. And this is the only definition that will make sense with the rest of math, basically. And everything works. So it's really beautiful how this is basically another right way to think about complex numbers. Remember, we were thinking about complex numbers as r cosine theta plus I sine theta. That was one of the ways we could represent complex numbers. There's the polar representation. Now, this has a form this is called exponential form. And you can write this as just e to the log r plus I theta, because it's e to the log r. E to the log r is just r, times e to the I theta, which is just cosine theta plus I sine theta. This is another way to write any complex number as e to another complex number. Okay. Why is this interesting? Well, remember that complex number multiplication thing? It's obvious now. If you try to multiply two complex numbers, r1 and theta1, r2 and theta2, you just multiply them as these are exponents. So the exponents add. That's what happens if you multiply e to the something and e to the something else. You get e to the sum of the exponents. Now the logs give you log of the product of the radii, and the angles just add together. That immediately proves the formula for multiplication of complex numbers. No need for any of this sine addition formula, cosine addition formula. You immediately get this. If you're multiplying two complex numbers in trigonometric form, the radii multiply, you get r1, r2. The angles add, angle 1, angle 2. Done. This is the reason why I said that this had a beautiful proof before. And so the right way to think about complex numbers is often exponential form. So the question, is Euler's formula an axiom? You can think of it as sort of the definition of e to the I something, but also, yeah, you can sort of think of it like that. It depends on exactly what your axioms are. I wouldn't call it an axiom so much as a definition, because you need to define things if you're using terminology like I for the first time. Okay. So what else can we do with this? There's a thing called Euler's identity, which is what happens if you plug in pi. If you plug in pi, you get cosine of pi, which is -1, plus I sine of pi, which is just 0. So e to the I pi equals -1. This is sometimes called the most beautiful formula in math. And it's often written like this. And this is sort of a reason why it's the most beautiful formula in math, because it relates arguably the 5 most important numbers in all of math, which is e, I, pi, 1, and 0. It's just really great. Mathematicians love this. There's a question. So it's because the definition of what complex numbers are is a thing such that the formula works, which feels really weird because usually numbers are defined really simply, like adding one to another number. I'm not exactly sure that I can answer that. Basically, the only thing you need to define the complex numbers is just knowing that I is the square root of -1. And from that, everything else can follow. You can show that everything is consistent. We didn't do that, but you can show that everything is consistent. What are the complex numbers is a question. It's a really good question. The complex numbers are a completion of the real numbers, so that if you have a real polynomial, all of its roots are numbers, but they're complex numbers. That's how you get the complex numbers. There is a notion of sort of completing a set of numbers so that you get additional, so that all the polynomials have solutions within that set of numbers. And if you complete the real numbers to the complex numbers, then any complex polynomial has complex roots. You don't have to go even larger than that. Now, to get into the details of why that's the case, there's abstract algebra involved. And there are things called groups and rings and fields. But suffice it to say that that is what's going on. It's basically so that you have solutions to polynomials with complex coefficients having solutions to polynomials with real coefficients having complex values. Happy to talk about them more later. Okay. Now let's quickly go over the roots of unity with Euler's formula. We had roots of unity. We saw them as in this form: cosine times an angle plus I sine times an angle. The roots of unity are the solutions to x to the n minus 1 equals 0. And geometrically, they look like this. The angles, for example, for n equals 6 are 0, 2 pi over 6, 2 pi over 3, 2 pi over 2. This is like all the multiples of 2 pi over 6. This. Okay. And they all lie in a circle because they're all at radius 1. Now, in exponential form, you can just write them like this, which is where the angles go into the exponents. So you have 2 pi I over n, 4 pi I over n, all the way up to 2 times n minus 1 pi I over n. And then 1 is always a root of unity. 1 to the n minus 1 is always equal to 0. And that's just e to the 0 pi I over n. Because 0 pi I over n is just 0, and e to the 0 is just 1. So this is just the same thing as the roots of unity before. It's just if you wanted to write them differently. And many people will write them like this, so I just wanted to give you another way to write down the roots of unity. Okay. And now let's finally solve the problem at the start of class. What is the limit as x goes to 0 of e to the x minus 1 over sine of x? And how would you do that? What are your thoughts? So first thing when you see a limit is just try plugging in the number. What happens if you plug in the number? You get e to the 0 minus 1. That's 1 minus 1, so 0. And then in the denominator, you have sine of x, so that's 0. So you have 0 over 0. 0 over 0 could be anything again. So this limit is not clearly any particular thing, but like sine of x over x, it could be something cool. It could be like 0 over 0 could be anything from infinity to 0. Let's see what it is. There's a suggestion to write the Taylor series. Let's use the Taylor series. So this is the Taylor series for e to the x. If I took away the 1, so e to the x minus 1 is just subtracting the 1 from the Taylor series. So I get all the other terms of the Taylor series, and then sine of x is just this. What do I do next? Why did this help? Factor out x. Great, let's factor out x. We can divide both sides by x. We have this. Now what do I do? Oh, now we do the thing. Whenever you have a limit, try just setting the thing equal to 0. Let's set x equal to 0. If x equals 0, all of these terms cancel out. All of these terms cancel out. And we just have 1 over 1. Done. Oops, sorry. Done. I got a little overenthusiastic. So the limit is just 1 over 1, which is 1. This would also be a way now that we could prove sine of x over x. The reason why I didn't use that is because we were actually using it to prove the derivative of sine of x. Could we also use L'Hopital's rule here? Better than that, this is a proof of L'Hopital's rule. This is why L'Hopital's rule is a thing. So L'Hopital's rule says that if we want to figure out the limit of function of x over function f of x over g of x, if f of x and g of x are both 0, how do we do it? Well, what we can do is we can write down the Taylor series. We can write down the Taylor series for both f and g around 0. And since f of 0 and g of 0 are both 0, we can take them out. Then we can cancel x. And then if we set x equals to 0, all of these other terms die away, and we just get the derivative of f over the derivative of g at 0. That is L'Hopital's rule. If you have two functions where they are both 0 at 0, and you want the limit of their ratio at 0, then you can take the ratio of their derivatives at 0. And it also proves a stronger version of L'Hopital's rule is if you wanted to do if this was still 0 over 0, then you would see that there's an immediately another thing you could do, which is just take the derivative again, because you kill these, and then you divide by x again, and then you get the double derivative. So you can just keep on doing it. And yes, there is a version if you're at infinity instead of going to 0. OK. I am happy to stick around for a couple minutes for questions. Next time, we will look at probability, and that will be on Wednesday of next week. Have a good Thanksgiving, everyone.